shouldn't be too big
Yeah.
of a problem.
Are you comfortable with setting your notes?
Yeah, I can do that. I just have to remember.
Okay, I can remind you. As long as you're comfortable with sharing your notes.
Yeah, I could also refer the reader to Lawson-Michelson because
Yeah,
that's
but that's what I'm saying. If you write big for this one, it'll be fine.
How's that?
Okay. Good.
That's the book I got one shot at one.
Oh, the one we were talking about?
Yeah.
Good?
Is it recording already?
Yeah.
Okay, so welcome back to the seminar, or to the first time to the seminar. This is going to be the first in probably a series of talks about Clifford algebras, because we talked a lot last term about fiber bundles and K-theory and all of that cool stuff. And Clifford algebras are very relevant to physicists and geometers, and they have a very intimate connection with K-theory through something called the Atiyah-Bott-Shapiro isomorphism. And that's hopefully going to be our main goal for this whole seminar. But other things I want to talk about, because it's a physics seminar, are things like what do physicists mean by the Spinor Bundle when you have a spin manifold. So we're going to have to talk about the representation theory of Clifford algebras. But today we're just starting with the basic structure and definitions of these objects so that everyone can get familiar with them before we go and do more complicated stuff. And so the kind of canonical source in modern days is the very first chapter of Lawson-Michelson. They just go through the whole formal theory of Clifford algebras and their representation theory and classification, and then prove the Atiyah-Bott-Shapiro isomorphism for the end of the first chapter. So this book is famous for being about index theory. It's sort of like the book about index theory that algebraic topologists like to advertise, and so that's me. Okay, so let's start out by fixing conventions. Lawson-Michelson do everything as general as possible, and then they fix some constraints on the field whenever they need to. And this involves a little bit more work. It's not super complicated, but for our purposes, we're just going to fix real numbers or complex numbers, because we're doing physics or geometry, and that's all we'll ever need to think about. And there's other reasons that we'll run into almost immediately for wanting to consider just these fields. And we're going to talk about finite dimensional vector spaces over this field. A lot of this stuff also works in infinite dimensions, but there are a lot of important results that only work for finite dimensions, so we're just going to not bother bouncing back and forth, and we're just only going to talk about the finite dimensional case. And the third little ingredient that we're going to use, which is probably or possibly the new thing if you're studying this for the first time, is the notion of a quadratic form on your vector space. So a quadratic form has these two conditions. It's a function from v to k that sort of behaves like the function x squared on the real line or the complex line or any field. So the first condition we're going to want is that it scales quadratically. Given any scalar in our field and any vector, we pull this thing out with the square. And the other thing, we want it to behave like x squared, right? So if we look at what happens if you add two things under x squared, well, we know this is not a linear transformation in general. You get x squared plus y squared plus some error term, 2xy. So if you're in characteristic 2, then this 2 goes away and you get x squared plus y squared, which is a weird case, so we're actually going to avoid characteristic 2 by restricting to these cases. So as you can see here, when you square this out and subtract away x squared and y squared, like we're doing here, then what you get left is this bilinear form. And so in fact, so this motivates this condition here. I'll try not to make those look like minuses.
Oh.
Yeah, those are not minuses. So this is actually a source of many bilinear forms. So if we fix source of many quadratic forms. So if this is a bilinear form, and we're going to use notation a lot and use Q for a bilinear form and for a quadratic form, but you'll see why in a moment. Then QV we can define to be just take our bilinear form and apply V twice. this is quadratic. And moreover, so if we take our quadratic form Q, apply it to V plus W, right? So by definition, it's this. I forgot to add a condition. So notice that when we say that this is bilinear, if you look at this, this is also symmetric. If you change the role of V and W, you get the same thing. So if instead we start with a bilinear symmetric form, when we take this expression, we expand it out. Just like you normally would with any bilinear form. Now these two things are equal if we assume that it's symmetric. So we get a QV, which is supposed to be like a V squared, plus QW, which is like our W squared, and then our error term is 2 times QVW. So if you start with a bilinear form, and you construct a quadratic form out of it by just applying the same variable in both entries, then you find that the original bilinear form shows up as an error term for checking linearity. And since we're working over R or C, we can invert 2, and we can define the polarization. So definition. So if Q from V to K is quadratic, its polarization is defined to be QV is just 1/2 QV plus W minus QV minus QW. And again, this expression doesn't even make sense if you're working over characteristic 2. So thankfully we get to avoid that. And so away from characteristic 2, we actually get this correspondence between quadratic forms from V to K and symmetric bilinear forms. So this is actually a bijection. Given one of these, you get a K by that formula, or a quadratic one by that formula. Given a quadratic one, since we can invert 2, we uniquely get the symmetric one by this formula. So this is a bijection. So a lot of the time we're going to bounce back and forth between our quadratic form and the polarization and sort of treat it like the same entity. Okay. That's the end of the first part. Well, first page. Okay. So let's look at the property of quadratic forms. So let's say like this. So if we take a bilinear symmetric form, which I'm going to start writing abbreviated SymBil, symmetric bilinear, we're going to define this to be non-degenerate. If basically we treat this as kind of a pairing, right? So we can take our Q, V's, and W's, and we can sort of see how these vectors pair together. If we have a particular V that pairs to 0 with every W in our vector space, non-degenerate should mean that this is a check to determine whether V is 0 or not. So in other words, the only vector, so i.e. if QV is defined to be the linear operator, just given by sending a W to its pairing with V. So then non-degenerate means QV is the 0 operator if and only if V is the zero vector. So this is what we mean by non-degenerate. And we say that, so if we have a quadratic form, so we define this to be non-degenerate if its polarization is. So it's not quite as easy to check. It doesn't mean that Q is non-zero in every vector, but it means that if you pick any vector and take the linear operator that's defined by plugging in a W in the other coordinate, then this operator is non-zero. There's some value for which it gives us something non-zero. Okay, so the point, maybe we'll look at an example just to show that I'm not talking crazy. So let's take V as R2. Our bilinear form, a symmetric bilinear form, could be represented by a by a symmetric matrix. And we're going to take this symmetric matrix. So that we've chosen in terms of the standard basis. So V equals V1 E1 V2 E2, and W equals W1 E1 is W2 E2. Then our pairing between V and W is equal to V1 W1 minus V2 W2. And so in particular, well, this is a claim, is that this is non-degenerate. You can check. This is a non-degenerate bilinear form. But if you apply your quadratic form to, for example, the vector 1, 1, then we're getting 1 squared minus 1 squared is 0. So there's still plenty of vectors where you actually get the value of 0 for your quadratic form, even though the bilinear form is non-degenerate. So don't make that confusion. Okay. One thing to note, before I jump into the next lemma, so the 0 form is degenerate. In fact, for every vector, right, the associated bilinear form for this quadratic form is just the 0 form, where you have 0 in every entry. And so for every V, the corresponding linear operator is 0. So this is sort of a maximally degenerate form. So in particular, if you take a contrapositive, so a non-degenerate form, I have to write bigger, is not 0. So that's just an immediate observation. Okay, so this is all great. Let's get to something that has some meaning and power. So so we still have a finite dimensional vector space. Q is a non-degenerate quadratic form. Then there exists what I'm going to call a Q basis. What I mean by this is we have a set of vectors E1 up to En. Which are orthogonal with respect to the bilinear form for Q, and also give us non-zero values for each vector. So Q of EI is non-zero for all I. And if you take two orthogonal vectors, two different indices, you get a 0 here. Or you can write this more succinctly if you want. Ui Uj is equal to delta Ij times Q Ei. Okay, so Lawson-Michelson just state this at the the start of a proof in the second section. They just say choose a basis with this property, because they assume that everyone's already really familiar with quadratic forms.
That one might be a little too far.
This one's too far.
Yeah, are you comfortable with only using these guys? Yeah.
Yeah, sure. What about that one over there?
That one is fine, that one's
Okay.
fine. It's literally just that one, it's too grainy.
I won't use that. Sure. Easy. I could even use a red chalk to put an X through it. Okay, so let's prove this because it's actually really cheap. I had to think about it and then I figured it out. Okay. So, since our form is non-degenerate, we can always choose a v and v so that q of v is not 0. This is one thing that non-degeneracy buys us. So that's a good start. We can start with our basis E1 should be equal to this element where q of v is not 0. What did I say? Yes, okay, just non-zero. Now, well, that's pretty good. We want to apply induction somehow to peel off a one-dimension lower subspace and find a q basis for that, and then extend it by this. So what we can do, yeah, what's the most succinct way to say this? Okay, we're going to do this by induction. So the base case is n equals 0, so that the empty set, I almost wrote brace brackets around nothing, empty set is a q basis. So this is actually the base of our induction. So if n is bigger than 1, that means that we can find a v such that this is true. Otherwise, every v is just 0, and so there are none. So if n is equal to 1, we're going to do this. Now consider the space. We're going to call v perp. And this is defined to be the set of all vectors which are orthogonal to v with respect to this bilinear form. So I forgot to mention, I should have mentioned, that a really common bilinear form to consider is just the dot product on Rn. This is sort of the generating example, is the dot product on Rn. And the associated quadratic form is just the norm squared. So we want to consider these q's, especially non-degenerate ones, as being a generalization of what it means to be orthogonal and what it means to measure lengths. And so, for example, the Minkowski metric is given by a non-degenerate form that's a generalization of the one I wrote over there for R2. So we'll get into more signatures like that later. Just forgot to kind of motivate the idea between these things. So this is why I consider this set to be, in a sense, an orthogonal complement to the vector v. Okay, so if we did this, this is a subspace. This is a vector subspace. It's the kernel of QV, right? So it's a linear subspace, and what am I trying to say? Yeah. So we can, in particular, apply induction. The dimension is going to be smaller. We can make a Q basis for the subspace and extend it by E1. So the only thing we have to make sure is that the dimension of this is correct. So if the dimension of V bar is n minus 1, we are done by induction. So how do we verify that that actually is the right dimension? I thought this was going to be hard, and then it turned out to be easy. So, like I said, this is just the kernel of this operator. So consider QV going from our vector space to the base field. So this is a linear operator. And we know that V goes to QVV is not 0. So it's a linear operator onto a one-dimensional vector space, and therefore it's surjective. So by the rank nullity theorem, right, so we have a finite dimensional vector space. The dimension of V is equal to the dimension of the kernel of plus dimension of the image of this operator. And we just said that this image has dimension 1, and this guy had dimension n, so indeed the dimension of this kernel, which is the dimension of the perp, is equal to n minus 1, and we're done. So given a non-degenerate bilinear, or non-degenerate quadratic form, or a non-degenerate bilinear form, we can always find a good basis where all of the basis elements are orthogonal to one another, and their actual Q value is not 0. Okay. I feel like I'm really belaboring this. Does anyone have questions that they would like to ask so far? It's kind of just basic algebra right now. Okay, so here's a question. Can we normalize this basis? Use a Z. So i.e., so we have QV, say not equal to 0. So what we'd like to do can we find an A, some non-zero scalar, so that Q of this new scaled vector is equal to 1. So like when we have a dot product, we can make our vectors orthogonal and then use our norm squared function to reduce all of our vectors linked to 1. So can we do the same thing with an arbitrary quadratic form? And so we have, by definition, this is going to be a squared QV. So over an arbitrary field, this equation isn't necessarily solvable. So depending on what QV is, its inverse might not be a square. So for example, so if K is R, QV is minus 1, we can't do this. Because no matter, so if we have any, negative 1, or any negative number, I can just write it like this. If QV is any negative number, there's no positive number. Every square is positive over the reals. You cannot make it into 1 by multiplying with the square number. Even worse, if we took K equals Q, then you can have lots of things that don't have square roots, and you especially can't normalize there. But over K equals R, we can do QV is equal to plus or minus 1. So the best that we can do is we can normalize to saying, well, it's plus or minus 1. This isn't so bad. Like I said, over the rational numbers, you can't really do anything. Over finite fields, there's some very bad primes where you can't do anything either. But over the real numbers, you can at least get to plus or minus 1. And moreover, over the complex numbers, right, you can even, now negative 1 is a square. Now you can definitely normalize. And so we're going to say, right. So the conclusion is if K is R or C, then exists a, what I'm going to call a normalized Q basis. Where by normalized I mean i.e., so it's a Q basis in the sense that I just erased down there, and QEI is plus or minus 1 if K is equal to R, or if it's C, we're going to actually require it to be plus 1. So this is the result, this is the corollary of our normalization lemma that I erased, combined with the fact that we're working over a field isomorphic, well, R or C as our base field, is the ability to normalize bases like this. So that was just to justify why we work over these fields in particular. Okay, and to set up a lot of foundational stuff that Lawson Michelson don't really talk about. Okay, so now we can actually define what we're talking about here.
Hold on.
Yeah.
I mean, just wanted to see the middle screen. I just asked him if it's.
Sure.
I'm gonna wait till we're sure it's good.
Sure.
Hmm?
Sure.
Okay, he's not responding. Oh, he's speaking. Wait, I mean, say that again. Hello?
Is he coming through here? Is he speaking?
No.
He won't come through here because.
Okay, yeah, no, he's typing now. Yeah, he's good. Alright,
Okay.
good to go.
Okay, so now I'm going to get to the actual definitions of the talk. So we're going to define now, given a vector space, given a quadratic form, which we know behaves like this over the reals or complex numbers, we're going to actually define the Clifford algebra associated to this quadratic form. So the idea of this Clifford algebra is going to be, well, we're going to start with a free associative algebra over V. So this is just generated by products of vectors in V of various length, where when r is equal to 0, we're going to make the convention that this is a copy of our base field, which is R or C. So this is what happens when you take, you treat your vectors as elements in an algebra and just take kind of the most canonical algebra that contains all of those things. That's just the full symmetric, what do they call this thing? I call it the full tensor algebra. You take every length of vectors of length r, and you treat these as the additive basis for the underlying vector space, and you can multiply two tensors together by just concatenating them. And so we start with the free associative algebra, and then we define the Q ideal of this algebra. I'm going to write this as an I sub Q. It's contained inside the full tensor algebra. It's a two-sided ideal. And you generate it the following elements. So whenever a vector V gets paired up with another copy of itself, this is meant to be equal to the minus of the quadratic form. So we take all of these elements, and then we let the Clifford algebra, no, I'm going to give it more space. Okay. So we take all possible products of elements in V, and you mod out by those ones that say that the square of an element in V is determined by the quadratic form. So the Clifford algebra here so we're going to get CLVQ is defined to be tensor algebra modulo this two-sided idea. So the idea CLVQ is the algebra generated by V with the following relations. V squared, because it's an algebra, equals minus QV for all V and V. Okay, so you can match that up to what we had, unfortunately, on the other side of the entire blackboard, so the people watching are going to have a hard time seeing it. So we're just saying that everything squares to the negative of its quadratic form value. Okay? Sure. And then I want to mention in particular that inside this Clifford algebra there's an embedded copy of V. So if we let I sub Q specifically be this quotient map from the tensor algebra to the Clifford algebra, so the kernel of this is the ideal, the Q ideal, then pi Q is injective on the linear subspace tensor 1V. And so we think of tensor 1V as being an isomorphic copy of V sitting inside of our Clifford algebra. This is a really bad looking one, sorry about that.
What's the motivation behind the definition? Like why do you define the ideal as such? Like is there some geometric reason why you want that as a structure?
I can give an example. I think there's sort of a convention, you can choose plus or minus one, and then there's a sort of a dualization between those two conventions. But this is the convention that is common. So here's a great example. So I'll just mention the trivial example. So if V is equal to the 0 vector space and Q is equal to the Q form, then the Clifford algebra of the 0 vector space with the 0 form is just equal to the base field K, because you just get the tensor 0V left behind. I'll mention if Q is the 0 form, well, generally the Clifford algebra is going to be, right, so Q of everything is 0, and so our defining relation for the Clifford algebra actually gives us the alternating algebra back. And now let's look at a very interesting example. Let's say V is the one-dimensional real vector space. So I'll put R to the 1 to remind us that this is the vector space and not the field. And Q is the bilinear form, or the quadratic form given by plus 1. So it's just the usual multiplication. So i.e. Q of x, y equals xy. It's just, so the quadratic form is just squaring. Okay, then Clifford algebra of V, or rather R, with this quadratic form. How did I want to describe this? So, okay, yeah, I haven't said enough to really describe this. So this is a two-dimensional vector space. So what do we have in degree 0? Right, we have the unit 1 living inside the base field. In degree 1, we have all of the vectors of R1, and so a basis for that I'm going to take as E1. And then when we get to degree 2, we have products of vectors. Well, when we take products of anything in degree 1, they're all just linear multiples of E1. And so when you square them, right, so A E1 squared is equal to negative Q E1 A squared. This is equal to negative A squared. So in particular, when you take E1 squared, you get minus 1. And so we get an isomorphism. We get an isomorphism between this Clifford algebra with the trivial quadratic, well not trivial, but the product quadratic form to the complex numbers by sending 1 to 1, and we send E1 to the imaginary unit I. And so, yeah, this is an algebra isomorphism. So by choosing this convention, by taking this ideal and where you get, V squared is minus QV, one of the most basic examples that you come up with is actually just the complex numbers.
Okay.
So this is kind of one of the motivating ideas for thinking about Clifford algebras, is that they generalize the complex numbers. And while we're on examples now, we can get more. So for example, this gives us the complex numbers. Here's another example. So let's just extend this one dimension more. So in degree 0, again, we have the unit. In degree 1, we have now two basis vectors, E1 and E2. And in degree, so where E1 squared equals E2 squared equals minus 1. And then in degree 2, there's an element called E1, E2. So there's no relationship between E1 and E2. that's going to cancel anything off. So as a vector space, this is an additive basis. And in fact, you get an algebra isomorphism from this thing to the quaternions. And so 1 goes to 1, E1 goes to I, E2 goes to J, and then E1 times E2 goes to K. So they also generalize the quaternion numbers. And then if you put a 3 here, you might think that you get the octonion numbers, but you don't, because this is always an associative algebra, and the octonions are not associative. Yeah.
I have a stupid question, so feel free to ignore it if you think it takes too long. But why is Clifford of V and 0 the alternating algebra?
This is because the quadratic form, in that case, I will use that later. So where was the
Like
example?
plugging it into the definitions, I can't see why it's the alternating algebra.
Sure. So we can do that. So so if Q is 0, Q is the 0 form. So therefore QVW equals 0 and QV equals 0 for all V, W, V, right? And so the ideal IQ is then generated by the set of all V tensor V, but then instead of adding QV, you just add nothing. But this is exactly the ideal that you generate or mod out by to get your what's the right way of saying this? Yeah, it's not exactly the same ideal.
They're isomorphic.
Yeah, they would be isomorphic. So normally to make the exterior algebra, this is the tensor algebra modulo what? The ideal generated by things that look like V tensor W plus W tensor V. Right, so you want to enforce that there's an anti-commutation in this.
Right.
And so you just have to figure out that, you have to just show that these are the same ideal somehow.
Right.
Because you can pick V to be a sum of two things, I think, and then.
So going, this way is easy because, going this way is easy because you can take VW to be the same thing and then divide by 2. And then going the other way, how would you do it? You would just write V tensor V is like a half of,
Okay.
yeah.
Okay. Some clever rewriting of that. Okay.
Yeah, so you have to do the math and show that this ideal is equal to the ideal generated by these guys.
Okay. Perfect. Thank you.
Yeah. There's also a property that I've been skirting around that I should mention now. In particular, well, let's see. Yeah, so there's this commutation rule here that just says that these anti-commute. So there's a more general commutation rule for the Clifford algebra, which I'll give now. So we're still considering a vector space in a quadratic form. And then we get that in the Clifford algebra, so we can write this. Start with 2QVW, which we know to be, how do I write this? Q of V plus W minus Q of V minus Q of W. And then so that in the Clifford algebra, these are going to be minus V plus W squared as an element where this multiplication is now happening in the Clifford algebra, minus V squared minus W squared. If you expand this out, you're going to get V squared plus W squared plus VW plus W times V. I'm going to write this bigger. V squared plus W squared plus V times W plus W times V. and then we're still subtracting off v squared and w squared. So we get that cancellation, and we still get a minus here. So if we rearrange, what we find is that VW plus WV, well, they don't anti-commute, but the failure to commute is given by the bilinear form. So this is going to be minus 2QVW.
Plus is on the v squared and the w squared, I think, because v is.
Yeah.
Yes, that's right. And now this minus sign here, don't forget about that one. Yeah, that makes more sense. Okay, thank you. Yes. And then is this giving me a 2? Yeah, so this minus goes to that side. So this is sort of the fundamental commutation rule for Clifford algebras. And it gets used all the time. So in particular, if QVW is 0, so if they're orthogonal according to Q, this means that they anti-commute. So in particular, going back to the alternating algebra, QVW is 0 for every V and W, and so it's an anti-commutative algebra. Yes. Okay, so now given this, yes. So now I should mention there is a canonical vector space isomorphism from the alternating algebra on V to the Clifford algebra on V, given by choose E1 up to En basis for V. So this is going to be an additive basis is given by wedge products of elements in the basis, where the indices are strictly unequal. I'll say this is K, and they're strictly increasing. So this wedge product under this linear isomorphism just goes to the Clifford algebra product. And so I emphasize that this is, strictly speaking, a vector space isomorphism. This map does not respect the product on the algebras. If you take this and concatenate it with another one, and then rearrange to get the original expression, so yeah, I mean, it's okay. I don't have to explain it. So this is just something to be aware of, is that there is this linear isomorphism between these two, which means in particular that the dimension of the Clifford algebra over your base field K is equal to 2 to the dimension, where n is equal to the dimension of V. So kind of meant to mention this before I got into the examples. So the way that you can see that these maps actually do give you isomorphisms is by counting the dimensions. So this Clifford algebra, since this is 2-dimensional and this is non-degenerate, Clifford algebra has dimension 4. This is a linear vector space of dimension 4, and so that's how I knew that this was a basis, because I already knew what the dimension of this vector space was. Otherwise, I wouldn't have been able to conclude that that's an isomorphism. Okay, I feel like I'm taking a long time. But I really wanted to elucidate all of this really basic quadratic form algebra stuff. But we have to start getting into more real things. So there's a universal property for this construction. It goes as follows. So let F from V to A be a linear map where A is an associative algebra. Okay, so if f satisfies some condition, mainly if in A we have that f of v squared equals minus qv times the unit in A for all v and v, then there's a unique algebra homomorphism from the Clifford algebra of v, q to A. So this is an algebra homomorphism now. So that if you restrict it to V, remember that V was an embedded subspace of this Clifford algebra, is all of the products of length 1, that this is equal to the original function f on V. So I'm not going to go through the proof of this. This is one of the more like formal blah blah things. Dropping this. The idea is pretty simple. So if we have any function from V to A, you automatically get an associative algebra map from the tensor algebra to A, because it's the free associative algebra on V. If moreover it's a linear map and it satisfies this condition, it shows that the kernel, this IQ kernel, the IQ ideal is contained in the kernel of F. Is contained in the kernel of F, it would be contained in the kernel of the extension to the free associative algebra. So you get like an F tilde from the tensor algebra to A, and this condition says that, that the IQ ideal is contained in that kernel. And so it extends down, what's that word? Other opposite of extend, but not restrict. Anyway, it descends down to the quotient algebra, which is the Clifford algebra. So this is just formal stuff.
Can you draw a diagram of what you just explained?
Yeah, I'll do that. That's good.
So what does this buy you? Like, is it just kind of like a tool used in proving other things, or?
This property?
Yeah.
Yeah. So a lot of homomorphisms are really easy to define on V, and like you don't want to have to go through the effort of trying to construct something on the whole Clifford algebra. So if you have a nice enough thing defined on V, then you just get something for free.
Okay.
So the essential idea, so I'll go like this. So we have V. So here we have A. Here we have V. And here we have the full tensor algebra of V. So here's our F. And this will be like F tilde. So what F tilde does is, well, this full tensor algebra is a sum over all products of lengths arbitrarily large. So you come across some tensor product of length R, and all you do is you apply F to each of the things and multiply them together in A. So this is kind of why this is a free thing. You just have to decide what it does on each individual thing, and then you apply your function to each individual thing, all multiplied together in A. So this is how your F manifests, and then you go down to your Clifford algebra. This is not a short exact sequence. F tilde, where this product, I have to distinguish this product in A with the product in the Clifford algebra, so that, so F tilde, right, this gets mapped to Clifford algebra multiplication. And so F bar of the Clifford algebra multiplication is just going to be F tilde of whatever this was. And this is well defined because the indeterminacy goes to 0 in A.
And from the Clifford to A, that should be a bar, right?
Yeah.
Okay.
Yeah. Thanks. Yeah, so this is what's going on. It's kind of just applying two universal properties, one after the other. Okay, so for example, so here's kind of the main example. If F from VQ to V prime Q prime preserves Q, and by which I mean that for all v in V, Q prime of f of V equals Q of V. Then we get a map between the Clifford algebras. So on one hand, you think of Q prime as sitting inside its Clifford algebra, and then you check that this function preserves that ideal. So you get a function from the Clifford algebra for Q to the Clifford algebra for Q prime. And so in particular, if you let OVQ equals the set of all invertible F of fix Q, when Q is non-degenerate, this means that, so for every single one of these, we get an automorphism of the Clifford algebra. So this sits or embeds into the algebra automorphisms of this Clifford algebra. Where in particular, like invertible linear transformations that fix your thing, they go to units in the. Yeah. Okay, so in particular, I want to talk about a very special one called the grading operator. Okay, so for any V, we can always take the antipodal map, sending a vector V to its negative. And so this gives for us, this is going to preserve the quadratic form. So this gives us a function alpha, an algebra homomorphism from the Clifford algebra of V back to itself, where on a given product of vectors, V1 up to Vr, what we get is you just apply the negative sign in each entry, and you get negative 1 to the R times what you started with. Okay. So I wish I had more room on the bottom there. So the point of the point of alpha is that, I should mention, I can say right here, of course, alpha squares to 1. So because alpha squares to 1, since it's acting on this Clifford algebra, you can think of as a vector space. Well, it has an underlying vector space. Alpha generates a subgroup of order 2, and every vector in the vector space as eigen decomposes into eigenvalues for plus or minus 1. So we can let CL0 VQ be the eigenspace for alpha for eigenvalue plus 1, CL1 VQ equals the eigenspace for alpha with eigenvalue minus 1. And so we call these elements even, and we call these elements odd. And like I said, everything has an orthogonal decomposition. So in particular, so the Clifford algebra VQ as a linear space, so it's a vector space that decomposes into the sum of these two subspaces, where this one actually is a subalgebra. So we have phi becomes phi 0 plus phi 1. So this is going to be our notation for our even and odd parts of a given phi. So if you think about the alternating algebra, right, you have these homogeneous elements of each degree. And in that case, the odd elements are generated by things with an odd number of factors, and the even elements are generated by a thing with an even number of factors. But because we have this weird relationship happening in the Clifford algebra, an expression doesn't really have a well-defined number of factors, but the only relationship that we have, or the only relation we have, is if you see the same thing appearing twice, you can turn that into a number. So two of them disappearing or coming in preserves whether or not it's even or odd. And so that even and oddness is witnessed by this alpha automatically for us in a way that we just don't even have to think about decomposing things and counting how many factors. We just have this operator called alpha, and it has these eigenvectors. These eigenvectors give you this orthogonal decomposition, just like classical linear algebra. So this alpha is going to be very important for us. Okay, I just said a lot. Other questions about that? Okay. So this alpha, in fact, tells us that this is a Z2 graded vector space, or algebra. So it's important to point out, really important to point out, this is a Z2 graded algebra, meaning that CLI BQ times CLJ BQ is a subset of CLI plus J BQ, where I and J are in Z mod 2. Because some of the things that you would naturally want to do with an algebra, it turns out there's sort of the wrong way to think about it unless you take the Z2 grading into account. So this fundamental separation between even and odd turns into a very big subtlety. So in particular, we're going to finally get to the meat of the talk, adjoint representation. So the point of this is to have the Clifford algebra acting on itself, and we think about our vector space V sitting inside the Clifford algebra, and we find some certain special elements of the Clifford algebra so that their action actually preserves V. And so we find inside of our Clifford algebra like this very rich representation on the underlying vector space itself. Okay. So I'll say it like this. So we're going to consider a V in V, and where we treat this as being a subalgebra of this, or rather a subset of this, and we have a W in V. And so this is the common way to define an adjoint representation inside of an algebra. So I'm going to put a tilde on it, you'll see why. So the adjoint action of V on W is typically defined to just be, well, you take V times W times V inverse. So conjugation. Conjugation. So you want to define a conjugation action of the Clifford algebra on itself. And you want to call it the adjoint action, and I put a tilde on it, and we're going to see why. So by definition, it's this. So let's apply our commutation relation to V and W. So we're going to get a minus W times V minus 2 QVW, and then we're still times V inverse. Okay. So on one hand, we're just going to get a minus W because the V and V inverse cancel out, minus 2 QVW. Well, now what is V inverse? So we can do a quick calculation on the side. So V times V, V squared, equals minus QV. And by assumption, did we make this assumption? Not yet. Aha, not yet. So let's say that QV is not 0. So if QV is not 0, not 0, then we can divide through by minus QV and find that V inverse is just equal to minus V over QV. Okay, so as long as the Q value of V is not 0, we have an immediate expression for the inverse that we can just plug in here. So we get minus V over QV, right? And so we can write this out. Well, I'll write it like this. So in fact, if we take minus of the adjoint action of V on W, then what we get is W minus 2 QVW over QV times V. So if we were talking about the usual inner product on Rn, this would be the norm squared. And this expression would be reflection through the hyperplane orthogonal to V. So, but with this general bilinear product quadratic form, we've just generalized the notion of reflection, orthogonal to V. Okay, so this is our nice reflection, but over here we have this really annoying minus sign. So one problem now is that if our vector space is odd dimensional, the minus sign is orientation preserving, and so our adjoint action is always going to be the minus is orientation reversing in odd dimensions, and so the adjoint action with the minus on the other side is always going to be orientation preserving in those dimensions. But we want the adjoint action to be actually doing the reflection and not just up to sign. And so the way that we fix this is by amending our adjoint action using our grading operator to take the Z2 grading into account. So we define the twisted adjoint action, twisted, so the add without a tilde of, what are we going to say? Yeah, so this is going to be defined on all units of the Clifford algebra. So every multiplicatively invertible element to the automorphisms of the Clifford algebra, like algebra automorphisms. What it's going to do is take a phi, and it's going to spit out alpha phi blank phi inverse. So by introducing the alpha, we're going to get an extra minus sign whenever our things have odd degree. And so in particular, we're going to have the add v w is going to be the correct thing. It's going to be reflection through this hyperplane. So this is our primary tool for using Clifford algebras to study the underlying vector space using this adjoint action. Okay. So now I have to be a little bit quick because I don't have a lot of time left. So I'm glad I didn't prepare too much. So here we have some special subgroups. Okay, so notice that whenever we plug a V into our adjoint representation, and note also that this is a homomorphism. This is a group homomorphism from this group to this group. So whenever we plug in a V, we get a reflection. So whenever we plug in a sequence of V's, so a product of V's, we're going to get a composition of reflections. So this is preserving V. So any product of elements in V is also going to preserve V. I'm going to write this out. So let this be the set of V in V with non-zero Q value. And so in particular, we saw non-zero Q value means that these are all invertible in the Clifford algebra. So this sits inside the group of units. Yeah. Okay. Why did I put a star on that? Oh, right, pull back. Okay. So in particular, V in V cross goes to add V is an element of the general linear group of V, right? So this is a general linear group. So I claim it's even more than that. So if you take Q and apply it to add V W, so we're applying, so we want to see if add V actually preserves the quadratic form for every W. So if we do this and plug it in, and now we just kind of plug and chug. So this is minus 2 QVW over QV. V. This is a quadratic form, so you apply quadraticness. You get QW plus Q of minus 2 QVW over QV. V. And then plus 2 times the polarization. So we're going to get a W here and a minus 2 QVW over QVB. Okay, so this is still QW. This scales quadratically, so we get plus 4 QVW squared over QV squared, and now we have a QV. And then this is bilinear, so this just pulls out and you get a minus 4 QVW over QV, and this is a QWV. Okay, so notice that this QV cancels with 1 on the denominator, and that symmetry says that this is actually just 2 copies of QV. So this is also QV squared. So we actually just get QW back. And in particular, the adjoint representation applied to V is in the orthogonal group for this quadratic form.
How do you? Oh, you're missing a. Wait, what? How did you? So like you cancel those, but you have QV. Oh, never mind. I'm an idiot. Sorry, the QV cancels with the QV squared, and then
Yeah.
you're just left with yeah.
You still have 1 left
Yeah.
over. Yeah, good question. Okay. So, in particular, we have a homomorphism, a group homomorphism from, so for any V, this ends here. So if we let P, V, Q be the subgroup generated, subgroup of the group of units, so let's take generated by all vectors. So we're looking at V1 times up to VR, such that VI is in these invertible vectors. Then we get that the adjoint representation goes from this particular subgroup homomorphically to OVQ. So this is something that I'm going to put a big box around, because the whole point is that we found some subgroup of the group of units of the Clifford algebra itself, which has this natural orthogonal action on V itself. And so I promised I would construct pin and spin. So pin and spin are going to be subgroups of this guy that are sort of determined by their actions through OVQ. Okay, so, and then in particular, oh yeah, you can write down what this is. What this does, it takes this product of vectors and it spits out the composition of the reflections, where by definition I'm saying that rho V on W is this formula that we write down over there. I've written it down 2 or 3 times. Is it plus or minus? Minus it is. Never remember. Okay. Okay. So our adjoint action of this nice subgroup is acting on V through orthogonal transformations. Good.
So OVQ is the orthogonal group. I thought we had OVQ as something else earlier. Or it's erased now, but.
Yeah, I said at one point that OVQ, because it preserves the quadratic form, it gives you an automorphism from the Clifford algebra back to itself.
Okay, yeah.
So you can take this OVQ. So this kind of like, you can think about it that way as like these things in PVQ get mapped into OVQ, but then even farther they become like maps on the Clifford algebra and not just V. But you also know that they become a map on the Clifford algebra because the adjoint formula is defined at the Clifford algebra level anyway. Yes. Okay. What am I doing next? Oh yeah, so here's the classic result that you don't have to prove. These guys are smart. Bertrand and Giordane, they showed that if V is finite dimensional, Q is non-degenerate as always. So any element G in this orthogonal group of our vector space in our Q. I don't remember if they had any assumption about the field. I think this is actually a super general thing. So any element can be written as a product of reflections. As G equals rho V1, circle rho VR, where R is less than or equal to the dimension of the vector space. So the way that you would do it for a real vector space is you would note that, what do we say? So by Jordan normal form, you write this as a product of rotations, and each rotation over R can be expressed as a product of two reflections. And so there's at most half as many rotations as the dimension of the vector space, and so the reflections is also going to be less than the dimension of the vector space. So what this means, right, so if any element G can be written as a product of reflections, we can just take that product of reflections and make the product of those vectors in the Clifford algebra. And so we get that the adjoint map from our P group surjects onto O. So there are no orthogonal transformations which do not come from the adjoint action of something in the Clifford algebra. And so now, what's the kernel of that map? Okay, so here's a lemma, proposition even. So the kernel of the adjoint map restricted to P, I'll just say that adjoint map as opposed to this full one, is equal to the non-zero scalars. So the first thing actually you have to convince yourself is, number one, the non-zero scalars actually are a subgroup of PVQ. So why is this for the case of R or C? Because if you have any V equals negative QV, right? So you can always normalize your V to get plus or minus 1. But then if you can't get 1, you can always just take V times minus V. So we get all of K cross N. So anything in the non-zero elements can be written as a product of things from the vector space. So this is something that isn't true in arbitrary fields. And so a lot of what Loss and Michelson do is they work in another group called P tilde, which by definition is just all of the Clifford algebra elements that preserve the subspace. And then they have to, distinguish these two subgroups. And everything I'm about to say is they prove for P tilde, but the reason it isn't true for P is because K cross is not actually a subgroup in that case. So to go, yeah, probably didn't have to say all that. So I'm not going to do all the details for this because it's quite tedious. So here's the idea: is write phi into even and odd form. And then you write, so focusing first on the on the even. Write this as a combination, pick E1, En, a normalized Q basis. And then write phi 0 is equal to P1 E1 plus P2, where Pi are polynomials in E2 up to En. So because you can write anything as a sum of polynomials modulo some relations, write your even thing as something that doesn't have E1 in it plus something that doesn't have E1 in it times E1. So you take away your part that is divisible by E1 and factor out E1 to give you two polynomials that don't involve E1 at all. And then you apply some nice stuff. So what's the point? So this, so phi 0 even means that P2 is even and P1 is odd. And so if you apply a lot of these relations, so phi 0 times E1, here's the trick, is that phi 0 commutes with everything. So in particular, consider E1. So on one hand, if you write this all out, you get x1 E1 squared plus, sorry, this is going to be a P1 E1 squared plus P2 E1. This is minus Q E1. Probably shouldn't waste time, but I'm already doing it. Okay, so this just gives you a number. So you can move the number past the P1, you get this number. Here P2 is even, and so it commutes with all vectors. So you can write this. And then on the other hand, if you write this out, you get E1 times P1 times E1 plus E1 times P2. So those are the same. Now we want to move the P1 past the E1. Since we've chose a Q basis and P1 doesn't have an E1 in it, these just anti-commute. So this is a minus E1 squared times P1 plus E1 P2. But the minus E1 squared is equal to Q E1 P1 plus E1 P2. So these cancel out, and the fact that this is non-zero tells us that P1 is minus P1. So since we're not characteristic 2, P1 is 0, therefore phi does not depend on E1. So this trick, by using evenness and just fiddling around a bit, allowed us to conclude that this polynomial is actually 0. So our phi 0 doesn't involve E1 at all. And you can just repeat to get rid of the dependence on all of the other basis vectors, so that phi 0 has to be a non-zero scalar. And do the same thing with phi 1. It's similar but different. You find that both of the components are in K. They would then have to be K0 because this is a They'd have to be non-zero because this is a multiplicative subgroup. Okay. So I probably didn't have to spend that much time on that proof because there's more interesting things to talk about. Okay. So in any case, we've constructed a really nice subgroup out of products of vectors, and we figured out that it maps surjectively onto the orthogonal group, and the kernel is as trivial as it could possibly be. It's just the non-zero scalars. So those are the elements in our preserving subgroup, which just fix all of them. Okay. So now we're going to go look at our special groups that we're interested in, called PIN. Whoa, almost so close. So we have a group called PIN, and this is a subset defined to be a subset of P. So this is the set of all V1 up to Vk, so that, let's say that they're already normalized. So rather than just be any set of vectors, we're going to only take those vectors that are coming from the unit sphere, where the unit sphere is determined by what does Q mean. Spin. So like Cartan-Giordano says that every orthogonal transformation is written as a product of reflections. So reflections still work the same as they did in real space with the normal dot product. They still have determinant -1. And so the special orthogonal group, in particular, corollary is going to be that those are the products of reflections where you get evenly many reflections. So spin is going to be the analog of the special orthogonal group, where we're going to take products of things, and we're just going to say that this is in PIN, where K is just even. They each have Q norm plus or minus 1, but you only take evenly many of them. So these are the things that we've been building up to. theorem. This is the big important theorem that's relevant to physicists and geometers and topologists. There are short, exact sequences of groups. So trivial group going to F, going to pin EQ, going to O, EQ, and another short exact sequence with the same kernel, SO, VQ. So what's F? What's the kernel of this map? So in the real case, it's plus or minus 1. And in the complex case, it's the fourth roots of unity. Okay. Right. So let's see here. So the short exact sequence contains in it something we need to verify, which that both of these maps are surjective. So we've verified surjectivity for this P. So now we need to verify surjectivity for pin and spin. And so the idea here is that if we write any G in terms of reflections through some vectors, you can scale those vectors and you still get the same reflection. So you can change V however you want up to scaling by non-zero elements of the field, and you'll still leave G intact. And so going from pin spin to, so from P, yeah, how do I say this in English words? I'll say what I do here. So if G in OVQ is written as reflection through V1 VR, and suppose we normalize so that VI prime is lambda I VI such that Q lambda I prime is equal to plus or minus 1. So this is something that we can always do over the reals or complex. Then we're going to get that rho V1 prime circle rho VR prime is equal to rho V1 circle rho VR, and this is G. But this is now, of course, the adjoint map of V1 times VR prime, to where now, of course, V1 prime times up to VR prime is in pin. Right? So we started with some arbitrary vectors. Oh, I didn't do this, right? I have to do like this. Started with some arbitrary vectors whose reflections describe G, and then we said, okay, we're working over R, so we can normalize to plus or minus 1, and then doing this normalization to get us into pin doesn't change what our image was under the adjoint, because the kernel of the map from P to O is equal to the non-zero vectors. And so this is telling us, yes, the pin really is surjecting onto O. And similarly, well, actually easier, now that we've already done that, it's easier to see that spin surjects onto SO. The only difference between spin and pin is the number of factors that you have, and the only difference between SO and O is the number of reflections that you have. So that gets us surjection. Why is F the kernel? Why do we get this F? And then we have to stop. Okay, so why F? So let phi equal V1 up to VK in pin such that phi is equal to the identity element. So then what do we get? So we can take phi squared is equal to V1 up to VK times V1 up to VK. Oh, I didn't do this right. Hold on. I might have to bail here because I'm out of time and I realized I did this calculation wrong. Yeah, so you can't just square it, you have to introduce the norm. Yeah. So, yeah, I left out this detail, yes. Whoops. Knew I was gonna get something wrong. So you have to introduce something called the norm to make this work. So the norm goes from the Clifford algebra back to itself. And what it does is it takes a phi to phi times alpha phi transpose, where it also have to introduce a transpose. So this is sort of like a quadratic form that introduces the enough twisting and transposing in order to generalize the Q on vectors. And you'd also get that it generalizes square on the underlying quadratic or underlying field. So yeah, so I might end up getting to this next time to actually complete this proof. So you have to introduce this so that you end up getting that, yeah. The long and short of it is that you get that phi squared equals plus or minus 1, and if this is in K, if phi is in K, this is why phi is in K, because it's in the kernel of the adjoint operator. So phi squared being plus or minus 1 means that you can only get that kernel in the real and complex case. So, mangled that proof, unfortunately. I feel like I mangled a lot of it. Okay, yeah. I wanted to talk more about the real case, but I spent more time talking about basic stuff. So the next time I'm going to talk about the real case, and I'm going to start talking about classification and decomposition theorems, and talking about the volume element and how it gets used in order to split up certain representations, or even the algebra itself in some cases. But today I feel like the thing that I really wanted to hammer home was that we get this pin and spin groups as subgroups of units of the Clifford algebra, and they extend the normal orthogonal rotations of real space into something larger, where if you're looking over the reals as the base field, you get this interesting double cover that has a lot of interesting topological properties that I should mention next time as well. I don't have enough time right now. So it's possible that this might go from 3 talks to 4 talks. Okay, I will stop there. So thank you, and please ask questions if you have any. Questions?
If you guys have any questions,
Yeah, I can hear.
you can hear me?
No,
I should be able to hear, so yeah.
If you can get them from there.
Yeah, but I don't think anybody has any questions.
Okay. And I'll try to remember to take pictures and post the notes. But
Yeah.
some of them are great. They still have that mistake that I had over there. So
I think for the most part, the boards are very visible. It was just this one was starting to get a little iffy,
okay,
but yeah, for the most part, it was pretty good.
good. Yeah. Didn't get through as much as I wanted, but that always
Where
happens.
did you want to end?
I wanted to restrict to the case where V is or Q is positive definite, because we're actually, yeah. What am I doing here? Why is this different? Yeah. Instead of thinking about like an arbitrary Q, fix an actual representative with like R pluses and S minuses, and like describe the topology.
Can I see that page?
Yeah, that's not a good one.
No, I just want to see something. It was like the one, okay, because like, we talked how you can write, well, I guess you erased it now. You could write anything as like a product of reflections, right? That was the Cartan.
Yeah, Cartangent and
Yeah, but like the output of it was just sorry I pointed there because that was just where it was. But the output of that map that we had defined from P to O was like the output was already a product of reflections.
Yeah.
So how does it not follow directly from just the construction of that map?
How does what?
Because you said everything in O could be written as a product of reflections. Is that right, or am I mistaken?
Mm-hmm.
So, and then we have this map here that takes you, no, I'll still ask you, but in the light that I might sound really stupid, we have a map, we define a map which takes you from P to O that outputs a product. So all the elements of the output, like all the possible outputs of that operator are already products of reflections.
Yeah, I think I see what you mean. Just write it down to see if that's...
So that's what I'm wondering, like why, does that theorem not just follow directly from that?
So you're saying like we have P, which by definition is just given by products of vectors?
Yeah.
And you have the adjoint representation going from this to that?
Yeah.
Where it's right, it's an algebra homomorphism, so if you have a composition of stuff downstairs, you're just composing the resulting things. And then we saw by that calculation that this was exactly just reflection from these vectors. Yeah, so you
like,
have...
does it not follow directly from this?
well, what is it that you're trying to...
That everything in O can be written as a product of reflections?
well, you don't know that the adjoint map is surjective. So I used that theorem to verify that it is surjective.
Oh, right. It would be circular if you,
Yeah.
I forgot.
For sure, every O orthogonal transformation is two.
Yeah.
reflections.
Mhm.
Yeah. I see I missed the surjection part, yeah.
Okay.
That checks out.
Cool. Yeah, there's a lot of really tricky arguments when your field is not the reals are complex, but when you have the reals and you can just say that, oh, you do this, and then like it completely trivializes it.
The other thing is, what does R3 comma Q or plus one the matrix?
Oh.
What? So you said it wasn't the Artonians, but what is it actually?
Yeah,
I didn't want to ask them because in case it was complicated, but
Yeah, I don't know yet. So
Okay.
this is like contained in the classification part.
H plus H maybe?
It could be H plus H. Yeah, it's going to be an 8-dimensional space,
yeah.
vector space. But it could be also like the complex numbers.
It's probably just like a sum of either complex real or H, no?
Yeah, that's pretty much how it works. But sometimes you actually get matrix groups.
They're usually matrix groups of
So it could
CO, CH, or
Yeah.
R.
Yeah,
Could-
because
it
I
could be
remember
like
we proved in
2
representation
by
theory
2
that
complex
you can only,
matrices.
sorry,
It
go
could
on.
be 2 by 2 complex matrices or something that has the right dimension over R.
Okay.
So yeah, I have to like.
One of them is like H plus H. It depends on the signature. Like one of them. Is
Oh,
H
like
plus
if it's
H,
plus
one of
one
them is
or-
like C2.
Yeah.
Okay, well,
So like there's like tables in the book.
yeah.
So
Oh yeah.
So I'm looking forward to actually learning this for the first time because I never.
I can't believe, wait, what was the theorem for
I think you
representation?
make all these isomorphisms between certain Clifford algebras, and all of that you can fill out the table.
Yeah.
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 What was the theorem in representation theory where it was like you could
Yeah.
only decompose certain representations as like HC?
There it is. It is H
H plus H?
Yeah,
Yeah.
this one is H plus H. So like I'm hoping to actually present like how
Sorry,
to
what's
do this.
M sub n? What's this?
Oh, that's something
N by
else.
N
That's gonna be
No, it's like a weird script M sub n.
that's like the isomorphism classes of modules over CLN.
Oh, sure,
Yeah.
okay.
Yeah, and then if you take the ones that extend to CLN plus 1 and then quotient them out, you get K theory or something like that.
It always relates. Do you mind if I see that book again?
Yeah, sure.
This is like awfully clean.
Yeah, it was until I just touched it a bunch.
Did you get this from library? No, you bought this.
Yeah, I bought that a while ago.
Is that on Basil's writing? No.
No, I think we have similar writing.
Really? On the board is different, but on paper it looks relatively similar.
It's an expensive book, no? I remember looking
Yeah.
up, it's like $200 or something.
Yeah,
Oh, it
I think
even
I was
goes to
like,
the K
I was
theories.
working when I bought it, I think.
Yeah.
I deserved a gift.
Yeah. No one on the Discord has any questions?
No, I stayed for a little bit, but no,
Okay.
it doesn't seem like anybody has any questions.
Cool.
I should really try rereading that book. I tried to read it stupidly in first year of my undergrad.
Dude, I thought